Hi everyone, my name is Iza Sazanita and I am the instructor for this topic. Now let's start the lesson.
Chapter 2. Discrete time, linear time invariant. Impulse response.
Students will be able to differentiate the impulse response for a recursive and non-recursive system. Obtain the impulse response sequence from a given difference equation. The system we deal with in this topic is linear and time invariant. So, let's recall from the previous chapter. From the previous chapter, we learned that in a linear system, there is no operation such as power, log, cosine, and sine is allowed, satisfies the superposition principle. In time invariant, its input-output characteristics do not change with time or variables must not be accompanied by any mathematical operation except plus and minus. Thus, what's left is the LTI system that can be represented as a weighted sum of input and output sequences called a difference equation. System representation? In system representation, there is difference equation and impulse response. Difference equation represents LT system in terms of its input and output signals, while impulse response represents an LTI system based on the system transfer function. The transfer function of the LTI system is called the impulse response because when the system is input with an impulse signal, the output of the system is the transfer function. What is a difference equation? A difference equation is a mathematical way to describe how a system changes over time using a sequence of input and output values. It tells you how to calculate the current output by looking at previous outputs and current or past inputs. Imagine you have a signal going into a system. This is called the input signal. The system processes this signal and gives you an output signal. The difference equation explains how the system creates each new output value by combining two things. 1. Previous outputs, each multiplied by a specific weight, how important that previous output is. 2. Current and previous inputs, each also multiplied by a specific weight. This is an example of a difference equation being used in a system. It shows how the system calculates the output signal by using the input signal with specific weights. The output at any time is equal to the input at that same time, plus 2 times the input from one step before, plus 2 times the input from 2 steps before. 1. The system receives an input signal, represented as a short pulse that starts at time 0. 2. It keeps track of that input and also looks back at the inputs from earlier times. 3. The system multiplies each of those input values by a specific weight, in this case, 1, 2, and 2, 4. Then, it adds all those results together to produce the output. In this system, the input at the current moment is multiplied by 1. The input from one time step earlier is multiplied by 2. The input from 2 time steps earlier is also multiplied by 2. So the system gives more importance, or weight, to the recent past inputs. Why only input terms? There are no past outputs involved in this equation. That means this is a non-recursive system, it only relies on input values to generate the output. There is no feedback from the output itself. This system creates its output by looking at the current input and the last 2 inputs. It adds the current input, twice the input from 1 step ago, and twice the input from 2 steps ago. Each input is scaled, or weighted, before being added together. The result is the current output of the system. Next is impulse response. In an LTI system, instead of the input and output signals, the transfer function T, E is also represented as a discrete signal called impulse response, HIN, which acts as the weight to the input and output sequences. Thus, designing the discrete LTI system, the transfer function, is a process of finding or fine-tuning the weight values. The impulse response is the transfer function that describes how an LTI system responds to an input. To find the output, we write y of n equals t of x of n. Now, since any input x of n can be written as a sum of impulses, we write y of n equals t of the summation from k equals 0 to capital M, of x of k times delta of n minus k. Because x of n is the input and we are applying the system t to each shifted impulse, we can say that t of dot, the system, actually refers to the system's response to delta of n minus k. In other words, it's just responding to each impulse. Okay, let's look at what impulse response means in a linear time invariant system. We start with this equation, y of n equals the summation from k equals 0 to capital M of x of k times t of delta of n minus k. This just means, we're calculating the output y at time n by adding up all the input values x of k, multiplied by the system's response when it gets a short impulse at that position. Now, t of delta of n minus k just becomes h of n minus k, so we simplify the equation to y of n equals the summation from k equals 0 to capital M of x of k times h of n minus k. Here, h of n is what we call the impulse response. That's because when we give the system a special input, the delta signal, its output is h of n. So in simple terms, impulse response shows how the system reacts to a single blip, and we can use that to figure out how it reacts to any full signal. Now, usually, signals go on for a long time, so we extend our equation to cover all time. That gives us y of n equals the summation from k equals negative infinity to positive infinity of x of k times h of n minus k. You'll also see the same thing written in another way, y of n equals the summation from k equals negative infinity to positive infinity of h of k times x of n minus k. Both forms are the same, just flipped around. Don't worry, we'll prove this later in the convolution section. But for now, just remember, impulse response is the system's reaction to a single blip. And convolution is how we build the full output using that reaction. Now let's walk through the steps to find the impulse response of a system using a difference equation. We're given this equation, y of k plus a times y of k minus 1 plus a2 times y of k minus 2 equals b times x of k. Step 1, replace the input. We replace b times x of k with x sub I of k. That means we assume the input is an impulse signal, so x sub I of k becomes delta of k, and y sub I of k becomes h sub I of k, which is the impulse response. So the equation becomes, h sub I of k plus a times h sub I of k minus 1 plus a2 times h sub I of k minus 2 equals delta of k. Step 2, solve the characteristic equation. Now we solve the homogeneous part of the equation when k is greater than 0. That means we set the right side to 0 and solve. H sub I of k plus a times h sub I of k minus 1 plus a2 times h sub I of k minus 2 equals 0. The characteristic equation is, r squared plus a times r plus a2 equals 0. From that, we find the roots, r equals r and r2. Then the general solution is, h sub I of k equals a times r to the power of k plus b times r2 to the power of k. Step 3, find the initial conditions. Now we need to find the values of h sub I of 0 and h sub I of 1. Start with k equals 0, h sub I of 0 plus a times h sub I of negative 1 plus a2 times h sub I of negative 2 equals delta of 0, which is 1. But both h sub I of negative 1 and negative 2 are 0, so we get h sub I of 0 equals 1. Now with k equals 1, h sub I of 1 plus a times h sub I of 0 plus a2 times h sub I of negative 1 equals delta of 1, which is 0. Again, h sub I of negative 1 is 0, so we get h sub I of 1 plus a times 1 equals 0, which means h sub I of 1 equals negative a. Step 4, solve for a and b. Now that we know h sub I of 0 equals 1, and h sub I of 1 equals negative a, we can plug these into the equation from step 2 and solve for a and b. In the impulse response, we have recursive and non-recursive. For a recursive system, to find the impulse response, some steps need to be considered, as mentioned in the previous slide. The step is known as the classical method. Meanwhile, a non-recursive system, the impulse response is the weight of the input sequence. Note that this is only true if no past and future output is the non-recursive system. Thank you, and see you in the next video.